Thank you very much, Problem. And let me go ahead and share my screen with you guys with this one. Okay, right here, present now. Okay, I haven't used this a lot, so how am I going to share my screen with you? Let me see. Hmm. Okay, sorry, I don't choose what to share.
Yeah, I asked you as a co-hoster.
Okay, let me see if I can figure this out. I've never done that. Okay, got it. Okay, please let me know if you can see uh, my screen.
Yeah, it's very clear.
Okay, very good. So in that context, let me start sharing this with you, folks. And please feel free to ask any question at any time. So the topic is smart proxy modeling, which is using artificial intelligence for proxy modeling for numerical simulation models. In that context, let me quickly tell you what I'm going to cover. The fact is, I it's about 1 hour till 12. It's 11 by now, my time right now. And let's see how much of this I can cover. The amount of time is a lot. The amount of the topics that I have covered are a lot. But let me go ahead and tell you first, I'm going to talk to you about AI-based reservoir management, which AI has done reservoir engineering, so the managers can use in a very good fashion compared to what they have done in the past. With reservoir engineers, reservoir managers, usually there's a problem. Now this is going to solve that. There are two ways of doing that. One is AI-based reservoir simulation. I call it top-down modeling. I'm not going to cover that today, but if you're interested, we can. I can talk about it a little bit if you're interested. And the other one that I'm going to cover today is AI-based proxy modeling of numerical reservoir simulation, which I call it smart proxy modeling. And then I'm going to talk to you about what is the proxy modeling, the traditional proxy modeling, before the AI-based proxy modeling. What we have done in the past about 40 years on proxy modeling in petroleum engineering and also in any other engineering that use numerical simulation. There are two of them that has been created in the past several decades, and one is called ROM, Reduced Order Model, that they uses mathematics to do that. The other one is called Response Surface Model, RSM, which is using traditional statistics to do that. And I'm sure you know that many of the current numerical reservoir simulations, such as CMG and others, they have this statistic version of it, the RSM, in their software, and allows you to do. I'm going to talk about that as well and tell you what the difference is between these technology that have been developed 40, 50 years ago and been used versus what has been just generated through artificial intelligence. Then I'm going to talk to you about smart proxy modeling in more detail. There are two ways we do deal with that, and I'm going to show you the result. One is cell-based smart proxy modeling. I'm going to explain to you what that is. The other one is well-based smart proxy modeling for numerical reservoir simulation. I'm going to go through those and provide you what they mean, and then actual case studies. I'm going to show you to show you how is smart proxy modeling using artificial intelligence. What can it do? And I think that would be very important to everyone. Excuse me. So in that, first and foremost, let's talk about AI-based reservoir management. And it uses these two different technologies. Let me start by mentioning that reservoir management requires to perform field development planning, uncertainty quantification, and optimization of oil and gas. However, they need to do that quick with a lot of speed because they have to make many tests in order to come to a conclusion, and what they're dealing with should be also accurate as much as possible. That is one of the reasons that numerical reservoir simulation that we use currently, although it's a great technology, but reservoir management sometimes have an issue, and I'm going to explain to you what that is, and that's how AI is going to solve it. So this smart proxy allows reservoir managers to use numerical reservoir simulation, CMG, Eclipse, T-Navigator, any of them, in a very, very good fashion, and very, very with highly speed and accuracy of exactly what the model does. So as you know, we start with a geological model. In numerical reservoir simulation, the first thing that happens, any company that works with it, they first go and provide the seismic survey if they have it. If they don't have it, of course, they're not going to do that, but they do well logs and core analysis, all these field measurements that comes from the reservoir. They gave it to a GNG expert, and they first and foremost provide a geological model, and then they provide that to the reservoir simulators. And the reservoir simulators go ahead and use that geological model in numerical simulation. And of course, beside those field measurement that I mentioned, they also start using the completion and injection history and production history and so forth. I'm sure hopefully you've been exposed. I've been teaching numerical reservoir simulation for the 25 years, and I'm sure you guys are exposed to it. It's a great technology, been used about 63 years in our technology, in our industries and universities. So once numerical reservoir simulation is done, then it is given to the reservoir managers or to the company to come to a conclusion, and computational time and expertise is enormous. Literally what it means to build the numerical reservoir simulation in every company in the world, it's going to take at least 2 years to do that, including geological model and numerical reservoir simulation and history matching and forecasting and so forth. And also, when they finish it, let's assume that you're doing a big field that you used few millions of cells in to build the numerical reservoir simulation. In that context, even if you use a lot of computers together to do this, it still takes several hours for the numerical reservoir simulation to run and provide the results. And since a lot of reservoir managers want to use this model and run it hundreds of times to come to a conclusion to what to do and what not to do, that's usually a problem for them, and that's why they mention they have an issue sometimes with reservoir engineers. Now, what this technology is going to do, as I'm going to show you, is going to allow this happens for the reservoir managers. It allows the CMG, T-Navigator, Eclipse, Petro, whatever reservoir simulation that is made, then it can run it instead of hours, it can run it literally in a few minutes. And it doesn't need tens or 40s of computers to be connected together to do it for 4 hours. You can do it on your laptop in 2 minutes immediately. And another beautiful about is that the smart proxy generates the same results of the numerical reservoir simulation that it was built to create proxy model from it. It allows you, it gives you everything that the CMG does or Eclipse does, or because it uses those numerical simulations that have been done. And it can generate over 95% accuracy of the results of the numerical reservoir simulation. And I'm going to show you the results. And of course, in that context, if you look at it, the field measurement that is used are as it's shown here. However, there's another technology that if you want, it should be another presentation that I have shown it to you. And that is called top-down modeling. What top-down modeling is, it uses a lot more field measurement that it's not used in numerical reservoir simulation. Well constructions, well tests that has been done, well workovers and operational and the surface facility issues, all of these measurement comes and it's done it's called artificial intelligence reservoir simulation and modeling, not numerical reservoir simulation and modeling. But that's another technology we can talk about that, but later on, not today. And another thing that you need to know, and I'm sure you all know, that the SWOT proxy uses that geological model that was provided to the numerical reservoir simulation in order to do that, of course. However, keeping in mind, the top-down modeling does not require a geological model. It actually generates a geological model itself. It's called geoanalytics. It's a technology that's it's provide geological models through artificial intelligence. And that's another, again, technology. But this whole thing, both of these technologies goes to reservoir management, and it allows the reservoir management to do OPEX optimization and CAPEX optimization. But in OPEX optimization is choke setting modification, wellhead pressure and gas lift and water and gas injection modification in order to increase production. And CAPEX optimization is identification where to drill the new well in order to producer or injector to increase production. So in that context, this has been the results of 30 years of research and development from my side that generated these two. And again, today I'm going to talk about smart proxy model. So reservoir analytics in the top-down modeling, which I mentioned, I'm not going to give you a lot of information, but just tell you what the difference is. It's a field measurements only, nothing else, and it uses top-down modeling. And I explained when I have to present this technology why it's called top-down modeling, and it can it does reservoir simulation hundreds of times quicker and faster than numerical reservoir simulation, and its result is better than that. It's purely on AI. It's a reservoir management tool, and it has a very, very small computational footprint, and it can be run on your laptop or even on your tablet and smartphone if you want it. And TDM is a tool for field development planning. But again, that's something we have to talk about later. However, in smart proxy modeling that we are talking about today, it's numerical reservoir simulation, Eclipse, Powers, CMG, T-Navigator, whatever, all of that, you get the data from there. You need only a few runs of that model, not hundreds, but only from 5 to 15 maximum. And then you put the smart proxy model replies numerical reservoir simulation at wells and at cells level, and it generates all of these results. And as you can see, these three, you have pressure distribution at 2 different layers. This is by CMG, and this is by numerical. Again, all of these are by numerical model. This is saturation for a model. And just quickly show you the result of it in a second, but SPM is a reservoir management tool. It has very small computational footprint, and it can run in a laptop or even on a tablet. And of course, it is a tool for field development and so forth. But very, very quickly, this is what smart proxy is going to generate, and you see how common or similar it is to the CMG. And you can see, compare them together. I'm going to show you a lot of that as we move forward. That tells you how it works. So in that context, let's talk about, first and foremost, in order to make sense, why smart proxy modeling, AI-based proxy modeling, is good, and it does what it does supposedly very, very nicely. First and foremost, we have to go through traditional proxy modeling, what we have been doing in the past 50 years, and to find out what is the difference between artificial intelligence model development in engineering in general. Does it use mathematical equation, mathematics, No, it doesn't. Does it use statistics? No, it doesn't. It's very, very different. So, but anyway, let me go ahead and tell you what the traditional proxy modeling does. There are two of them. One is reduced order model. The other one is response surface modeling. One is purely based on math, and the other one is purely based on statistics. So first and foremost, let's talk about proxy modeling. Upstream oil and gas industry has released this shortcoming of the numerical reservoir simulation, the large completion footprint, decades ago, right? However, we developed proxy modeling to address this shortcoming. We wanted to make it faster. The same model that takes a long time. The proxy model allows that the objective was to run that model, but provides the results much quicker, much faster, and can be used efficiently for reservoir management purposes. So we have not been very successful in this, both in those two proxy modeling, and let me explain to you why. So traditional proxy models can be classified in two categories, as I mentioned. One is mathematics-based, one is statistics-based. The mathematics-based is called reduced order model. The statistics-based is called response surface model, RSM. The ROM, reduced order model, simply, what does it do? How does it make the numerical reservoir simulation to run a lot faster? The way it does it, one of the major things that it does, not only for numerical reservoir simulation, for any reservoirs numerical simulation throughout the engineering. What it does, it simplifies that physics, mathematical, physical problem that has been used to build the numerical simulation. Because all of you know that the numerical reservoir simulation has quite a complex mathematical equation that cannot be solved directly, but it has to be solved through numerical simulation. However, one of the things that ROM does, it simplifies that mathematical equation so it can run and solved much quicker. However, it also can reduces the resolution of the numerical simulation in space and time. What does that mean? That means instead of having 5 million cells, 2 million cells, it could have only a few hundred cells or a few thousand cells. And in time, instead of going every second at the beginning and then become changed to hours, then changed to days and so forth, it from beginning to the end, it just does it in either in month or in year. So it reduces the resolution in space and time. And that's how ROM works, reduced order model. However, the RSM, response surface model, it uses the results of several hundreds of simulation runs, then uses statistical regression to fit it to a certain curve. That's what it does. It doesn't change the mathematical equation to make it quicker and softer. What it does, it allows you to run, and to be honest, talk to people who have done that in our industry. Once I told them that we do numerical reservoir simulation only with 8 or 15, up to 15 maximum ever we have done, 20, never more than that. Numerical reservoir simulation runs to do that. They were so they didn't believe a word. And I said, why don't you believe it? And they say, because we've been doing it for many, many years, and we have to do it at least 200 and sometimes 300 runs to do this. And it was very interesting to me that they do that. And they applied not to the entire system, numerical reservoir simulation. It only applies to a single location in space to do that. So anyways, let's talk about reduced order model. It's complex physics requires a small grid blocks. Grid blocks are what I'm calling it, and we call it cell as well. In order to accommodate proper convergence of the numerical computation that are used to solve the complex nonlinear and high-order partial differential equations involved in the fabric of some models. And in order to reduce the computational footprint of the numerical reservoir simulation, the reduced order model, that's known as ROM, usually incorporates one or both of these things. One of them is to the main physics, as I mentioned earlier, that was used to build numerical simulation, reduce that, simplify that, and then usually modeling physics, physical phenomenon includes some simplification and some time to use fudge factor. And in ROM, simplification dramatically increases through that process. So that's number one. Number two is they attempt to reduce the model's resolution, as I mentioned, in the space and time. Sometimes they accomplish this, they must incorporate a reduction in the physics of the problem of the well. So response surface, the other one, which is the statistic fashion technique in our industry, uses traditional statistics. What I'm saying traditional statistics, because statistics goes back to 150 years ago that was developed, data driven, that it does. It's very, very different with artificial intelligence. I have written a book that's going to be published soon in March that explains all of that in detail. And it has nothing to do with AI. So the main differences between traditional statistics and artificial intelligence, both of them using data, don't forget, are much deeper than some may know or believe and or admit. They're very, very different. So their main differences between these two, traditional statistics and AI, stem from their philosophical approaches to problem solving. For example, the difference are so deep seated that they may be referenced to the things that happens between Aristotelian logic, Aristotelian view of the world, and Platonic view of the world. And the traditional statistics approach requires no domain expertise. So in other words, what I'm trying to say, if you want to solve if you go to statisticians and ask them to solve a petroleum engineering, they don't need to be a domain expert of petroleum engineering. They just do they get from you. And there is the traditional statistics have no understanding of the main physics and geology behind the problem and a predetermined mathematical equation. And they don't go through all of that. So they actually use mathematical equation to do that, at fitting the data generated by the numerical reservoir simulation to the predetermined mathematics in order to do what they have to do. And you can see it in RSM if you get involved with it. It only applies to a single space, by the way. It doesn't go to the entire field that numerical reservoir simulation built. But anyway, so very quickly to finish this, smart proxy modeling is unlike ROM, reduced order model. Why? Because it does not simplify the physics of the numerical simulation, and it does not reduce the numerical simulations in space and time. That's the difference between ROM. However, how is it different from RSM, which is response surface modeling through statistics? AI does not use statistics, curve fitting, okay, to find correlation between few input variables and some of the output variables only at a certain time to certain location using hundreds of simulation runs. That all of this is done by RSM, which AI smart proxy modeling does not do that. I'm going to go to the detail of what smart proxy is developed how. Again, it is developed for well-based and cell-based. So first and foremost, let me compare this traditional numerical reservoir simulation modeling and AI-based numerical simulation. So in both cases, that's the issue that you have to know, that in both cases, the number of models, the model includes millions of the grade blocks. So in AI, we do not reduce that. It also uses the same number of millions that the numerical simulation uses. And then a single run of the model takes tens of hours using HPC. However, in AI, when we do that, it doesn't do that. A single run of AI-based model takes only a few minutes in a laptop, not an HPC. HPC has 40, 50, 100 computers. That's why it becomes fast. 3 days to 5 or 10 hours. And finally, this traditional numerical reservoir simulation makes uncertainty quantification and optimization almost impossible. Why? Because the model has to be run hundreds of times, and that's why reservoir managers have a problem with it. However, the same numerical reservoir simulation that has been built with CMG or Eclipse or Petro or any T-Navigator, when AI does a proxy of that, then yes, you can run that CMG, that Eclipse, millions of times only in a few hours in order to do optimization and uncertainty quantification. It does exactly the same thing, much, much, much faster. So smart proxy modeling of numerical reservoir simulation can be used in two parts. One is application to the newly developed numerical reservoir simulation, which is smart proxy of the newly developed numerical reservoir simulation using performing history matching to achieve better things. And of course, so right now we are at 11:30, so I cannot go any more detail of that. Why? Because then I cannot show you how it works. So I'm gonna pass these. This is tell you the smart proxies replacing the numerical reservoir simulation model, and it is higher than 95% accurate of CMG, Eclipse, and all that. It does it the same thing, and it's no simplification of the physics. It doesn't change the physics, and it doesn't change the number of cells, and it requires only a handful of simulation run, again, from 5 to 20, no more than that, and it allows you to do sensitivity analysis, field development, and all that. So one thing I need to tell you is the definition of that is the smart proxy modeling is teaching reservoir engineering to the open computer algorithms, which is called machine learning, using data from numerical simulation, CMG, Eclipse, and so forth. And the open computer algorithm that are used for the development of smart proxy modeling includes following machine learning. So what I'm showing you, we use artificial neural network, we use fuzzy set theory, and we use evolutionary computing, evolutionary programming, which is genetic, one of them is genetic algorithm. And also data from numerical reservoir simulation that we use is data that is built in the numerical simulation. However, one of the things that we do that is different than nobody else does is feature generation that explains or teaches to the machine learning algorithm the physics and the numerical solution of the numerical simulation. And I'm going to show that to you. And it is impossible to do this, the feature generation, if you are not a domain expert in the development of numerical reservoir simulation. And you will see that. Let me show you one more thing, then I'm going to go to the results. One thing that I need to let you know is that there are several wrong and negative techniques that companies and universities all around the world are currently performing to interact the numerical reservoir simulation using machine learning. This happened to me when I was involved in a recent project which had 7 universities, several companies, and national laboratories, and since the overwhelming majority of them were not petroleum engineers, and they were trying to do this for CO2, anti-climate change. And they were saying they were saying they're using AI, but their understanding of AI was literally nothing. And so they do not understand that there are differences between artificial general intelligence and artificial engineering intelligence. That's part of the book that I have written. You will see it. Using machine learning algorithms that have been developed for artificial general intelligence, such as convolutional neural networks, CNN, a lot of these things, they find it from on the internet, and using traditional statistics and calling it machine learning. And these are the problems that I was exposed to. And that's why I want to explain that to you, that this provides the information that some petroleum engineering departments, unfortunately, currently in the US, I know, but I'm pretty sure it's everywhere in the world, and large number of companies have very, very little or actually no understanding or information of what actual and realistic artificial intelligence is. That is a key issue that I wrote this book that is going to publish in March. And it's called Artificial Intelligence for Science and Engineering Application. So with that said, let's go ahead and show you the results of what the smart proxy model does. So for a reservoir management perspective, the main shortcoming of the numerical reservoir simulation model are their highly extensive computational footprint. So as you can see, no matter how fast your computational hardware or HPC, GPU, you cannot ask too many questions in short period of time. If you ask a question, if you want something to be done, it's going to take a long time to make several runs to come to a conclusion. And optimization's the same, and quantification is the same. And that's why we generated smart proxy model, and that's why other proxy models were developed in the past. So, excuse me. Let me finish this. I'm going to just show you the objectives of smart proxy modeling. It identifies the objective, smart proxy modeling. It designs a handful of simulation runs. It performs the simulation runs and generates the required data. And it develops feature generation, as I mentioned. I'm going to show it to you a little bit right now to teach the learning machine. And develop a spatial temporal data set, not only time, space and time, and designs the smart proxy model, and it does it through training, calibration, and validation to require AI-based model. And also another thing that we do blind validation. So again, to test the smart proxy model, we do not, to find out how good it is, we do not compare it with the numerical reservoir simulation runs that we used in order to build, to train, to calibrate, or to validate the model. We identify through blind simulation runs. In other words, we do 20 to train and 100 other runs of the same simulation run. We can test it to make sure how good it works. Excuse me. So run the smart proxy model of the time is the objective. It takes very quickly. So let me show you. We do it well-based and we do it cell-based. I think given our time, I cannot go through well-based. If you want, I can tell you, but let's talk about the cell-based, which is something that's very, very important and right now. So the cell-based smart proxy model, and remember I said we have to feature generation. Let me show it to you. So numerical simulation can have different types of cells, different types of cells. Smart proxy model can be developed for any type of cells. For example, here is an example. You can see the cells are not given when we do that. This happens actually in not numerical cells or something, but in CFD. However, in numerical reservoir simulation, as you can see, the size of the things is different and interact with them. That's no problem at all. Or it could be like this. Again, no problem at all. It works with all of smart proxy modeling. Let me show you one thing. In smart proxy modeling with cells, right? So every single cell is the issue that they have. So if this, let's say you have 2 million, 5 million cells, every single cell we model one. So if this is a cell, then the cell that is right next to it, they're communicating with each other, right? So that is something that you have to communicate with the machine learning. Literally, if you have, you're dealing with the communication of the cells. So if this is a focal cell, if you have one step is, we call it tier 1 offset cells. As you can see, this is offset cells that communicate with each other directly, right? However, the line communication, these are plane, the entire plane communicate with each other, you see? The entire plane communicate. However, sometimes there are not sometimes, but there are cells that do not communicate each other with the focal cell through the plane, but they do it through the line. So here it is. This tier 2 offset cell, doesn't this cell communicate with the focal cell, every other cell? Of course it does. How? First, it goes with that tier 1, and then it goes to the focal cell. We call it tier 2. Now there is a tier 3, that's the communication is through 3 steps, and it's a point communication. So here's the one. This is the third cell that still communicate with your focal cell. However, it doesn't do it like tier 2 or tier 1. Watch how it does it. First, it communicates with this one, then this one, and then this one. So this is a 3 steps before it goes to it. So the fact is, every cell that we model, we have to let this know to the details from the data. This is, we generate the data to teach the numerical to machine learning algorithm that we use in AI to tell them how to learn what numerical reservoir simulation does. And of course, then as you can see, as I said, step 1 is dealing with cells, focal cells. So this is the focal cell, and these are the offset cells. First, the offset cells that are dealing with it through the plane, right? How many of them are there? You can see, right? There are 2, 4, 6 of them, right? And then the plane communication is just like this. However, this one is the line one, not the plane ones, as I showed you earlier on one cell. And this is the point communication, as I mentioned to you. These are the 3 series of cells that communicate with every other cell, and that's what we have to communicate with the system. So quickly show you exactly the same thing. If this is the focal cell, then there are 6 cells that communicate with it with the plane communication, and we call it tier 1, right? The tier 2 are communicating through the line, and there's 12 of them, and you can see these 12 are communicating with every focal cell, the blue one in the middle, but they're doing it through line communication. And tier 3, the final one, is point communication. How many of there are? There are 8 of them, 4 and 4. So this is what very important to communicate. This is how you have to know what numerical reservoir simulation or numerical simulation in general does to communicate that or to teach that to machine learning. And then not only that, the rest of the things, let me show. Showing you in 3D, it's going to be tough. I'm going to show you in 2D, but it works in the reservoir. We do it in 3D, not 2D. So let's assume we just show you in one part of it. If that is the focal cell, then this is the night boring cell, right? And these are the offset cells, right? And then the key is, one of the things that's important, the distance of every single cell in the boundary. We have to tell that to the equilibrium, to the machine learning algorithm as well, to tell you where it is. And also, if there are production wells and there are injection wells, then every cell distance to these have to be also identified and provided to the numerical, to machine learning AI. And not only that, but keep one thing in mind. Imagine these are the cells, and this is the cell that we want, and here is the well. Just going the distance is one thing we do. However, if the well is producing not only this cell, but it's producing on these, all of these, or then you have to also provide this information as well. And also, it is important to note that this is the 3 wells we're dealing with. Also, then we have to deal with the cells that bring these production or injection communicated with these cells, right? So knowing all of that, for example, if the objective of the project is to identify the injection of CO2 movement in, as you all know, CCS or CO2 EOR, then the model should be designed in a manner to address the distribution of CO2 throughout this whole thing. So how do we do that? I don't want to go through too much detail, but this is how we do it. We go with pressure, we go with saturation, we go with the stress. So if you look with the pressure, we use these 3. In the saturation, then we use the pressure that we have developed already, and stress, we use both of them. So in that context, I'm going to stop this and literally show you some results. So 1 second, let me bring the other model. Here it is. Let me first and foremost find out, can you see this actually? How can I do this? Can you see my screen right now? Can you hear me?
Now, no.
Okay, I'm trying to figure out how to do this. Okay.
Doctor, the screen is not visible.
Okay, let me try to get out and get back in. Let's see.
So you just left the meeting. I think you have to rejoin the meeting.
Okay, let me 1 second. How do I? Because unfortunately I didn't do a lot of Google thing. That's why. So I'm going to share the screen again with you. Let me find out how to share it. Okay, here.
I think you can do it by using the entire screen sharing button.
Okay, so tell me if you can see it now. Can you?
Yes.
Yes, yes.
Okay, very good. So now I'm going to show you results, folks. Based on everything I told you that what we do, let me show you what happens when we do it. So this is an actual case study of smart proxy modeling that I have done, and I'm showing it to you. So here is a cell-based case study of smart proxy modeling. It has done on a DOE DOE project that we did for carbon capture storage analysis. Literally, this was the reservoir simulation that we were working on, that we got it from something that really happening in a state in the south of the United States. This was CO2 storage in saline aquifer, where the water is, not in numerical reservoir, and not where the oil and gas was before. And heterogeneous reservoir characteristics, as you can see, various. There are so many layers it has, and the layers are not flat, as you can see, go up and down. And grid block are not the same size. Every block, the size of the blocks are different, and you can see the same thing from another area. And the saline aquifer formation is our sands, and cap rocks are shale. As you can see, there are shale here, there are shale here, there are shale here, but everything goes right in between the 3 shale. So this is the same thing. It shows you that the CO2 is stored through 4 injection wells. These four injection wells that injecting CO2, and this is the size of the cells. As you can see, we had 65 layers, we had 125 grid blocks in 1 and 2 when you multiply them together. So this model in numerical reservoir simulation that we used, I think we used CMG to do it, that had 1 million grid blocks. And some of the reservoirs data are taken from citronelle field in a saline reservoir and in Alabama, United States. And one of the things, based on the data that we have, as you can see, there is several types of rocks. We use these 4 of them, rock type 1, 2, and 3. And as you can see, this is porosity versus permeability, and it tells you different types of rock that they had. So these are literally what it looks like. The top is a shale that nothing happens to it. Then below shale, there are 2 rocks, 3 and 4 rock type, and then there's another shale, and then below that there are 2 other type 1 and rock type 1 and 2. And then another thing is about these 4 cells in wells that we're injecting, and the injector wells are completed in all 51 sand layers. There was, as I said, there are 60 some layers, but some of those layers are shale. The injection doesn't take there, but 51 of them, the injection takes place. And the injectors well will be operating using 2 constraints, bottom hole pressure and max injection rate. So in that case, as you can see, we used 20 simulation runs. Each injection well has different injection rate and bottom hole pressure in each simulation run, in this 20 simulation run. As you can see here, what you see is injection rate, this is BHP, and this is the time, and you see every time they have a different amount. So because in every simulation, in 20 simulation, we have 20 rates and 20 BHP. They're not the same in every single one of them. As you can see here, they're different. In here, they're different. In here, they're different. So we have 20 simulation run. Each one has different amount of for injection and bottom hole pressure. And as you can see, how different they are. Okay. Now, what I'm going to show you is this: is that we started from 2020 to 2320 because we were in, it was for 300 years of numerical reservoir simulation. The key is from 2020 to 2050. This is the 30 years that injection would take place in the numerical reservoir simulation. And the 270 years after that, we wanted to see when the injection takes place, how the pressure and saturation goes throughout the entire reservoir. And in that context, as you can see, this is the pressure distribution and saturation, and this is what we will be dealing with. As you can see, there's 4 wells, and this is the saturation looks like. So one more thing I want to show you, and then the results, the geological realization. So generation of 20 geological realization took place, and 20 geological realizations. So not only the injection were different, but geological realizations were different for all the 20 that we used. Were generated to be used as geological model for numerical reservoir simulation. Each geological realization has different porosity and different permeability distribution. The sequence of the rock type along the reservoir layers and the relative permeability is the same for all the geological model. Here's an example. So out of the 20, I'm going to show you 4 of them. Just here, this is layer 5, that is right here, and you see in that layer 5, this is realization 1, this is 4, this is 19, this is 20. Every one of them, all the 20 are different from each other. This is layer 10, and then you can see that it's different. This is layer 27 on the bottom, and you can see how different they are, and layer 50. Right? And again, it comes from geological modelers that do that and say what possibility could be outside of that 4. And this is the porosity distribution. As you can see in different different simulators, you can see how porosity distribution is throughout. And this is a pressure distribution. You see how different they are. And then the result is we use numerical reservoir, numerical artificial neural network to do this. So important note is the fact is that fluid flow in the porous media is a function of time and space, not only time. A lot of people use LSTM, which is LSTM is exactly what we have been doing in numerical in petroleum engineering in the past several years, called dynamic conductivity map. It's just going one thing we do, which is only with the time. So it is very important not to use LSTM in a manner to avoid space and deal only with time. So please do not do that. That's not a good idea. So anyway, we have, the reason I'm telling you guys is because we've done it. For years we did it, and we finally came up to the problem that it has. So we're helping you. If you do, you eventually come to that problem. Anyway, in the next several slides, we compare reservoir pressure and CO2 plume distribution in space and time between CMG and Proxy model. The only difference is the Proxy model is in a few seconds. And the main comparison is not with geological realization and numerical reservoir simulation that were used to develop the. So in other words, what we're showing you are not the reservoir models or geological reservoir and realistics that we use to train the model. If you change it, that 20 goes to 100, and then you see the difference, what happens. So here's the 20 that we used. Out of these 20, you see number 5, 9, 13, and 17 was put out. These are data used for smart proxy blind validation. The rest of them, 16, were used for development of the model. So in the smart proxy development, we use 80% of every cells that we have here to train it, 10% for calibration, and 10% for also validation. I can go to the detail if you know what it is. However, these are never used in training AI at all. They were just used completely blind validation. Here's the result, folks. We do the training, we do evaluation, and then we do a deployment for that. Here's the result. What you're looking at on the left here is done by CMG. This is done by smart proxy. This is the error, less than 5% error. You see, there is less than 1% error. See how much it is. This is CMG smart proxy, and this is the error. This is the blind run, number 5, not the one of the runs that we used in order to do it. Now, I'm going to show it to you. This is 2020. Sorry, this is now 2021. This is 2022. You see the changes all the way to 2026. That was one. To go same thing, another layer. This is layer 21. Watch the difference between the two, and this is the error. 23, 24, 25, 20, 26. Now another layer, 53. CMG, smart proxy, compare them. See how nice it works. And now I'm going to show it to you here. I'm going to do it quickly, but you're seeing this is, again, a blind validation. This is smart proxy model was done not during the training and testing. This is layer 26 of geological reservoir 13 that was not used. We're going from February 2020 to December 2020 and compare these two. This is the, ready? Let's go. And you can see on the top here, it goes on the model monthly. And we do the same thing. Again, this is layer 8. And here, look at the difference. See how pressure goes in those two. Now here we go to another one. You can see it in, you see the changes? This is CMG, this is smart proxy model. And it tells you where it's doing it. February 2020, it's going through every single time step. This is another one. This is another blind run. Watch. It's going to go through every layer. This is another one, 2020. It goes through every single layer, goes down. See what happened. These are all about pressure. It tells you the layer. This is next one. See layers here, it tells you going through with layer. You see how less than 5%, actually less than 3% difference. Now, dynamic reservoir pressure that I showed you, 3 Smithsonian plot. Now I'm going to show you the whole thing rather than just the one layer. This is the entire layer, but you see, smart proxy, numerical reservoir simulation. This is error, 5% error if it gets red, but it's blue, it's less than 2%. Now here, the same thing, you're looking at from the bottom. All of these are pressure. And one more, again from the top, another blind validation, number 13. The same thing, looking from the bottom, again from number 13. This is the pressure. After this, I'm going to show you the saturation distribution of the 4 wells. What CMG does and what smart proxy, how exactly does it like that, but it goes far, far faster. Now, CO2 saturation. This is the number of, these are the wells. These are CMG. This is smart proxy. This is the error. The error maximum is 10%. Watch. We're going from January 23. Watch. This is another part. Again, you can see this is another one from 23 to 25 in layer 9. This is another one. And of course, again, this is another one. This is goes because they wanted, when we did the project, they wanted only between 1 to 10%. What we showed you was every detail percent, but this was only 10% that they showed. Now, here I'm going to show it to you. Sorry. Now here I'm going to show it to you as a video for the 3D, for exactly what you saw, the 4 injection saturation. This is CO2 saturation distribution in the entire reservoir. This is from the bottom, as you can see. This is from the top, bottom. Sorry, that was from the top. This is from the bottom. And this is again another one. This is the last one I'm going to show you. We're done with it. And if you have any question, any interaction, I can go through it. This is from the top and get completely blind validation. This is from the bottom. This is the last thing. And I'm ready to answer any question at any time if anybody has. Okay, I had well based as well. However, that did not work. So I'm gonna close this. How do I do it? Any question?
Thank you, Dr. Mohaghegh, and anyone have a question, can write on the chat box or unmute themselves. Yes, Mustafa, go ahead.
Thank you, Dr. Shahab, on this presentation. My question is, when you explain the actual case studies, you have 20 scenario for CO2 injection. Then you get on 20 geological realization. How you get on this geological realization? We know in every simulation run, you just change the injection rate and bottom hole constraint. How
Yeah,
you get on logical
sure, sure.
realization?
Keep one thing
Thank
in
you.
mind. Keep one thing in mind. The fact is, when you are injecting CO2 in the reservoir, right, and you only injecting 4 wells, you have created only 4 wells. What does that mean? That you have only 4 uh, well logs. So you know only for those 4 locations exactly what the porosity is. You can calculate permeability, gamma ray, all of that. So what happens with the rest of the reservoir? That rest of the reservoir, you don't have any information. And what the geologists do, they generate, they could be multiple different issues, and they you can have unlimited number of distribution of porosity, permeability, or anything else that you could have. That's why they actually generate 100 geological realization to say, okay, what if it's different? What if it's little? It's not 100% completely different. They have 4 people, 4 points that give them some information, but the geologists they could do 500 actually. The location of the well are okay, but the rest of them, you don't know it. Does that make sense?
Thank you. Thank you.
Sure, sure.
Sure.
Okay, if any other question, I'll be happy to answer. Then if not, then we can.
Hello, sir.
Yes,
Sir, you mentioned that do not use LSTM, which only focus on time and not on space. So which technology or which technique we use which focus on both time and space?
I'm sorry. Could you repeat that one more time? Say it again.
You mentioned that do not use LSTM, which only
Yes,
focus on time.
time, exactly. Okay.
So what is the alternate method to use which focus on space and time on both?
Sure. So in this, and this is actually, this fact is correct for everything we do for reservoir engineering, number one. Number two, now that we're doing it in smart proxy model, here's the question. Don't you think that the numerical reservoir simulation that has developed either with CMG, Eclipse, mm, T-Navigator, or anything, don't you think the generation of pressure and saturation, distribution of pressure and saturation, is it only about time, or it has to do with the static information, porosity, permeability, gamma ray, all of these things? Don't they play a role how to distribution changes? The fact is yes. And that's why we have to use that. And as the question that was asked with Mustafa, that how you do that, why you do that so many, and that's to me, that's not something what I do. That's what every company, they generate so many geological model, and those geological model only is about the space and static information. And that static information, it's going to be very, very, very important how the pressure and saturation distribution takes place. Does that make sense?
Yeah, yes, that makes sense, sir.
Okay.
Guys, if you don't have any questions, please fill the form, the presence form in the chat box, attendance form, please.
Go ahead, Abbas.
Hello, Doctor. Thank you for the great lecture. And I have a question, but it is kind of outside of this lecture. Is that okay?
Sure, absolutely.
What are the application of machine learning in the well testing industry?
Okay. So when you say well testing, the question is the well testing that they do in order to identify the production at the surface?
Yes, and the BV, also, what about the BVT analysis? Is there an application for that?
To be honest, I'm sure there is an application for that. That's not something I have been speaking and working with. If the companies are doing that and they come to us, we would be happy to deal with them. However, one thing is for sure that you have to know is those well tests that has been done, the key is they are actually measuring. Their assumption is low. The measurement, the fact that they do, is high. The key is we use those well tests in order to help how the model be developed in a correct fashion. That's number one. Number two, another two that we are right now doing for several companies through ISI, the company, not through university, is that the well tests, it's cost a very good amount of money for the companies. And if they have to do so many of them, then they have to pay more and more and more. However, one of the things we found out for several companies is it possible that we use the general measurements that takes place on an hourly basis, for example, can we use those to generate the well test based on the last so many well tests that have been done? We get the results from the well test, we use them as an output, and the input's going to be all other measurement. And we have already done that. So in that case, the number of well tests comes down. You don't have to do a well test per month or 300 well tests for the entire field that we have 500 wells. The number of well tests comes down, and you just, with AI, generate the same thing, the same result, and you test it with the well test as an output and as blind validation. Does that make sense?
Yes, that's great, actually. It does. Thank you for that.
Sure. Okay, there is no other question, folks. I strongly recommend to you to get exposed to artificial intelligence. It's a fantastic technology. It's going to change our entire world in the future. That's a fact. And it's going to also change what's going to happen in our industry as well. And any engineer, specifically you guys who are doing petroleum engineering, if you get exposed to AI, you become very, very, very happy in your life. However, please note that what you need to learn is the reality and the fact of artificial intelligence, not what some people do just to make marketing and money, and they don't really care how they're going to do it correctly or non-correctly. All right? Forget about the business part. Think about the science. Think about technology, and go through details of what AI is in general, what AI is in engineering, how different they are, and how fantastic they all are. If there is no other question, then we can say.
We have Safe.
Sure.
Go ahead, Safe.
To say.
Sir, have you tried transformer in reservoir simulation? Transformer. Have you tried the use of transformer in reservoir simulation?
What do you mean by transformer of reservoir simulation?
Transformer is AI.
Okay.
AI method. Attention is all you need. ChatGPT based model.
Yes. So, yeah. Keep one thing in mind. ChatGPT is a fantastic technology. I always tell all my students and my friends and people who work for me to use it. Go to ChatGPT, and that has been changed a lot for a lot of people. Now they understand how AI quickly can do a lot of things that we can do it, but it's going to take us a lot more time. Keep one thing in mind. ChatGPT it's a fantastic technology, but keep one thing in mind. There is another technology that's much, much better than ChatGPT. It's called Google Bard, which ChatGPT 4 that's going to be made very quickly. It's based on Google Bard. And there is another one called Microsoft Bing. These are all fantastic. However, don't forget, these are general intelligence. When they talk about engineering, they talk about it. They explain it. How? Why do they do that? How do they do that? The way they do that is because they are trained on papers, on articles, on books, and everything that has been written on the internet. Nothing else. Okay? Therefore, that's why they can explain a lot of things based on what they have been trained on in the reading of all these things. However, they will not be able to build a model of the physics. Don't forget that. For that, you need engineering application of AI. And if you want, some other time, I can show you. We have another technology that we developed. It's not a smart proxy of the numerical reservoir simulation. However, it is a AI-based reservoir simulation, which is not based on the one I showed you at TDM, that it has nothing to do with mathematical equation. It only uses actual data. And we know the actual data sometimes has a little problem with it. No problem at all. AI solved that too, and I can show it to you. And the key is it provides a model of the reservoir with as many wells as you have, as many time it has been doing. It does the same thing much, much, much quicker than CMG, Eclipse, or T-Navigator, or any numerical reservoir simulation. It does it much faster, it does it much quicker, and the results, it's far, far, far better, and it runs only in a few minutes. And it is purely, purely, purely based on your engineering application, your expertise in reservoir engineering, to be able to deal with it. And that's one of the things that we just showing it to a lot of company, and they're enjoying it very much. If you want, I can show that to you some other time.
Yeah, thank you, sir, for detailed answer.
Sure.
Who else has any questions?
So we don't have any question in the chat box and raise hand. So thank you, Dr. Shahab, and for this presentation and for accepting the invitation. Much appreciated.
It's my pleasure. Anytime.
Thank you. Thank you so much.
Thanks,
Great
Dr.
day.
Shahab.
Bye-bye.
Thanks, Dr. Shahab.
Have a good day.
Thanks a lot.
Bye-bye.